IEEE 802.11i-2004 or 802.11i, implemented as WPA2, is an amendment to the original IEEE 802.11. The draft standard was ratified on June 24, 2004. This standard specifies security mechanisms for wireless networks, replacing the short authentication and privacy clause of the original standard with a detailed security clause. In the process, the amendment deprecated broken wired equivalent privacy, while it was later incorporated into the published IEEE 802.11-2007 standard. Replacement of WEP 802.11i supersedes the previous security specification, wired equivalent privacy, which was shown to have security vulnerabilities. Wi-Fi protected access had previously been introduced by the Wi-Fi Alliance as an intermediate solution to WEP insecurities. WPA implemented a subset of a draft of 802.11i. The Wi-Fi Alliance refers to their approved, interoperable implementation of the full 802.11i as WPA2, also called RSN. 802.11i makes use of the advanced encryption standard block cipher, whereas WEP and WPA use the RC4 stream cipher. Protocol operation: IEEE 802.11i enhances IEEE 802.11-1999 by providing a robust security network with two new protocols, the four-way handshake and the group key handshake. These utilize the authentication services and port access control described in IEEE 802.1x to establish and change the appropriate cryptographic keys. The RSN is a security network that only allows the creation of robust security network associations, which are a type of association used by a pair of stations if the procedure to establish authentication or association between them includes the four-way handshake. It also provides two RSNA data confidentiality and integrity protocols, TKIP and CCMP, with implementation of CCMP being mandatory. The four-way handshake: the authentication process leaves two considerations: the access point still needs to authenticate itself to the client station, and keys to encrypt the traffic need to be derived. The earlier EAP exchange or WPA2 PSK configuration has provided the shared secret key PMK. This key is, however, designed to last the entire session and should be exposed as little as possible. Therefore the four-way handshake is used to establish another key called the PTK. The PTK is generated by concatenating the following attributes: PMK, AP nonce, STA nonce, AP MAC address, and STA MAC address. The product is then put through a pseudo-random function. To derive the PMK from the WPA PSK, the PSK is put through PBKDF2SHA1 as the cryptographic hash function. The handshake also yields the GTK, used to decrypt multicast and broadcast traffic. The actual messages exchanged during the handshake are depicted in the figure and explained below. The AP sends a nonce value to the STA. The client now has all the attributes to construct the PTK. The station sends its own nonce value to the AP together with the MIC, including authentication, which is really a message authentication and integrity code. The AP sends the GTK and a sequence number together with another MIC. This sequence number will be used in the next multicast or broadcast frame, so that the receiving STA can perform basic replay detection. The station sends a confirmation to the AP. All the above messages are sent as the APOL key frames. As soon as the PTK is obtained, it is divided into 5 separate keys: PTK, 16 bytes of EAPOL key confirmation key used to compute MIC on WPA EAPOL key message, 16 bytes of EAPOL key encryption key. AP uses this key to encrypt additional data sent to the client, 16 bytes of temporal key used to decrypt unicast data packets, 8 bytes of Michael MIC authenticator TX key used to compute MIC on unicast data packets transmitted by the April, 8 bytes of Michael MIC authenticator RX key used to compute MIC on unicast data packets transmitted by the station, The Michael MIC Authenticator TX or X keys provided in the handshake are only used if the network is using TKIP to encrypt the data. The group key handshake, the GTK used in the network may need to be updated due to the expiry of a preset timer. When a device leaves the network, the GTK also needs to be updated. This is to prevent the device from receiving any more multicast or broadcast messages from the AP. To handle the updating, 802.11i defines a group key handshake that consists of a two-way handshake. The AP sends the new GTK to each STA in the network. The GTK is encrypted using the KEK assigned to that STA, and protects the data from tampering, by use of a MIC. The station acknowledges the new GTK and replies to the AP. GTK, 16 bytes of group temporal encryption key used to encrypt multicast data packets, 8 bytes of Michael MIC Authenticator TX key used to compute MIC on multicast packet transmitted by 8 bytes of Michael MIC Authenticator RX key This is currently not used as stations do not send multicast traffic. The Michael MIC Authenticator TX or X keys provided in the handshake are only used if the network is using TKIP to encrypt the data. Security flaws. A major security flaw was revealed in December 2011 that affects wireless routers with the Wi-Fi protected setup feature, which most recent models haven't enabled by default. The flaw allows a remote attacker to recover the WPS PIN and, with it, the router's WPA2 password in a few hours. Users have been urged to turn off the WPS feature, although this may not be possible on some router models. It has also been claimed that, on some routers, the button that allegedly turns WPS off, in fact leaves WPS only and thus the router is still vulnerable. See also, Wi-Fi protected access, Wi-Fi protected setup, wireless security, WLAN authentication and privacy infrastructure, China's centralized wireless security method, references. External links, vulnerability in the WPA2 deprecated, hole 196, 1, 2.